Gases and temperature. We're going to take a look at Charles' law today. The Kelvin temperature scale is what we're going to use in lieu of the Celsius scale. This is because Celsius numbers can be a 0, which is problematic if you are dividing, because you cannot divide by 0, and they can be negative. I'll show an example of this when we get to our Charles law, okay? So absolute 0 is theoretically the lowest possible temperature that any material could ever get to on Earth, or the temperature at which the volume of a gas is 0. Now remember, to compress a volume of gas from, let's say, 1 liter down to half that, down to 0, these molecules actually do take up space. So can we ever get to 0? No, but this is theoretical. So theoretically, we can compress a gas all the way down to nothing. So what you're seeing here on this is that we have 3 different types of gas samples. And we've collected data for them. Let's say that this is hydrogen. So hydrogen gas is cooled from approximately close to 100 down to, let's say minus 30 degrees Celsius. Okay, this is the scale I'm looking at here. If we were able to continue cooling it, keeping the pressure the same, constant pressure, it will continue to compress itself. Okay, it will continue to decrease in volume until it reaches 0. Now, we did the same thing at the same pressure to, let's say, nitrogen gas here. We took some of its temperature values and we continued to cool it. And then we continued the line of best fit back, and it reached the same temperature when it became 0 volume. We did the same thing, let's say, with CO2 here. We cooled it, and then we drew our line of best fit with our data, and it intersected the graph at the exact same point for 0 volume. It came to 273. So no matter what gas we cool, they will all have a 0 volume at 273 degrees Celsius below 0. So they renamed that as 0 Kelvin. So negative 273 degrees Celsius is equal to 0 Kelvin. And they actually got even more specific there. It says negative 273.15 degrees Celsius. This is on the back of your periodic table in the defined or exact quantities. It's in the bottom right hand side of your periodic table on the back. Okay, it does say use 273 Kelvin, but I always use the decimal value here as well. So, again, this is theoretical. What happens to a gas as we cool it? Well, at some point, helium would have turned into a liquid and then into a solid. And nitrogen would have turned into a liquid and then a solid. CO2 would have turned into a liquid and then a solid. So technically, it won't be a gas anymore. But remember, this is theoretical. This is hypothetical land where we assume. All right. This is also the point where everything would stop moving. No particles would even be vibrating within a solid. There is absolutely no movement at all. Again, note that 0 is as low as you can go in Kelvin. There is no such thing as a negative temperature. So to convert between Kelvin and degrees Celsius, the temperature in Kelvin is equal to the temperature in degrees Celsius plus 273. The way that we get this, remember, was that 0 Kelvin is negative 273.15 degrees Celsius. Therefore, they just needed to add 273.15 to it. Note that there is a formula sheet available on our website. I have posted it on the homepage just underneath where you would find your periodic table. So let's convert the following temperatures. Remember again, the temperature in Kelvin is equal to the temperature in degrees Celsius plus 273.15. So first one, 0 degrees Celsius to Kelvin. So it's 0 degrees Celsius plus 273.15 is equal to 273.15 Kelvin. Now, technically, remember, for significant digits, when we are adding something with decimals, we choose the lowest number of decimals. So because 0 degrees has no decimals, we're going to round this to 273 Kelvin. 22 degrees Celsius to Kelvin. Again, we're adding 273.15, and we will get 295.15 Kelvin. One more time with significant digits. We have 1 decimal place here and 2 decimal places here, so we're going to round to 1 decimal place. So 295.2 Kelvin. And then we're looking at 524 Kelvin. We don't say degrees for it. 2 degrees Celsius. So we're going opposite here. So to get degrees Celsius by itself, I need to subtract 273.15 from both sides. So temperature in degrees Celsius is equal to Kelvin minus 273.15. So 524 minus 273.15 is equal to 250.85 degrees Celsius. Lowest number of decimal places, there are none on our original number there. So we get 251 Kelvin. Last one, negative 163.592 degrees Celsius. Add 273.15, and we end up with 109.557 Kelvin. Technically, Kelvin here is to 2 decimal places, or the conversion to Kelvin is 2 decimal places. So it wouldn't be incorrect to round this to 2 decimal places, but our measured quantity also has 3. So in this case, I would accept both answers of 109.56 Kelvin or 109.557 Kelvin. Those are both totally acceptable. Charles' law says as the temperature of a gas increases, the volume increases proportionally, provided that we keep the pressure and the number of moles of gas constant. This relationship between temperature and volume is said to be directly proportional because as one increases, the other increases as well. The formula is V1 over T1 is equal to V2 over T2, or V1 and V1 have to be volumes in any unit so long as they are the same, and T1, T2 must be temperatures in Kelvin. So here's where I can prove why we needed Kelvin. Let's say we had 1 liter of gas at, let's say negative 16 degrees Celsius. And then we're looking at if it is expanded to 2 liters, what is the temperature? Well, I'll put these in. So 1.0 liters for V1 over T1, and let's pretend that we didn't know about Kelvin. I'm going to put it in degrees Celsius, even though I know it's wrong, just to prove what's wrong. So T2 is what? To solve this, I won't rearrange my formula. What I'm going to do is cross multiply and divide because these are equivalent fractions. So we're going to multiply across where there are 2 numbers, and we're going to divide by the number that is opposite of our variable here. So negative 16 times 2 divided by 1 is negative 32 degrees Celsius. Now this is a problem. We said that as volume increased, temperature increased. But we saw that T2, so this one increased, T2 is negative 32. What? That doesn't make sense. The other issue is if we have a 0. You're going to see a bigger problem here. So let's say we had 1 liter at 0 degrees Celsius. And then we're going to raise the temperature to 25 degrees Celsius, and we're going to solve for V2 here. So 1 liter over our T1, which was 0 degrees Celsius, is equal to V2 over our 25 degrees Celsius. Cross multiply, we have 1 times 25, and divide by 0. Try and divide by 0, it's undefined. It cannot divide by 0, so we have an error. So the fact that we have negative values and we have zeros in our Celsius scale are a problem. So this is why we needed Kelvin. All right, examples here. An inner tube is filled with 2,000 liters of air on the hot Okanagan afternoon sun at 36.5 degrees Celsius. Alexandra decides to go tubing after dinner when the temperature is cooled to 18.3. How much has the tube inflated or deflated with this change in temperature? So let's list out what we know. We have the initial volume and the initial temperature. So 2,000 liters and 36.5 degrees Celsius. V2 is what we're looking for, and T1 we were given. Now, pressures weren't mentioned, so we can assume that they are held constant. The first thing we need to do is we need to convert our temperatures to Kelvin by adding 273.15 to each. So 36.5 degrees Celsius in Kelvin is 309.65. Now, because this isn't my final answer, I don't really care too much about significant digits when we're converting in a question. 18.3 converted is 291.45 Kelvin. So, we're going to look for V2, but we weren't actually asked for what is the final volume. We are asked by how much has the tube inflated or deflated. So we're looking for the change in volume. Okay. So we're going to solve for V2, and then we're going to look at what the V2 minus V1 value would be. Our formula, V1 over T1 equals V2 over T2. Again, I'm not going to rearrange this formula because it's equivalent fractions. It's nice and easy to solve without a rearrangement. 2,000 liters all over 309.65 Kelvin is equal to V2 over 291.45 Kelvin. For V2, we're going to cross multiply this way because this is where we have two values, and divide by the value opposite of V2. When we do this, I get that V2 was 1,882 liters. Remember, we're looking for the change in volume. So that is V2 minus V1. Always final minus initial when we're looking for a change. So 1,882 liters minus 2,000 liters is equal to a negative 118 liters. This means the inner tube lost, 118 liters of air. Because it's negative, it's lost. A birthday balloon is filled with 5 liters of helium at 22.5 degrees Celsius. The balloon is left outside overnight where the volume is measured at 4.75 liters. What was the overnight low in degrees Celsius? So our initial volume of the balloon was 5 liters, and the initial temperature was 22.5 degrees Celsius. V2 was 4.75 liters, and we are looking for T2, specifically in degrees Celsius. We need to convert our T1 into Kelvin first. 295.65 Kelvin. So V1 over T1 equals V2 over T2. Now, I will show you the rearrangement of this if you are not liking the cross multiply and divide and you want to actually rearrange your equation. The variable we're trying to solve for here is T2. It's in the denominator position of my fraction. So the first step in solving for T2 is actually to multiply by T2. In doing so, we cancel T2 in the denominator here, and it's now in a numerator position up top. Okay, we always solve for x equals, like, I don't know, 47 in math. We never write our final answer as 1 over x equals 47. Okay, so it has to be in a numerator position, not a denominator. Okay, so at this point we have T2 V1 over T1 equals V2. From here, it should be a little bit more straightforward to solve. We multiply both sides by T1. T1's cancel here. I'm left with T2 V1 equals V2 T1. And last step is to divide both sides by V1. And I'm left with T2 equals V2 T1 over V1. You can use that formula if you'd like. I'm going to sub back into our original, which was V1 over T1 equals V2 over T2. And I'll show you how they're the same. So V1 was 5 liters. And T1 in Kelvin. And we have V2, 4.75 liters, all over T2. Cross multiply these two. So to solve for T2, we multiply T1 and V2 together. And we are going to divide by 5 liters, which was our V1. So note how that's the exact same as our rearrangement of our formula. All right, 295.65 times 4.75 divided by 5. I get that T2 equals 280.87. Now, what unit is this? Remember, temperature values are always in Kelvin. We were asked for what it is in degrees Celsius, though. So to get to degrees Celsius, we need to subtract 273.15 from it. And we get that our final answer is 7.72 degrees Celsius. Final answer. Again, I had 3 significant digits in each of these values, so I'm going to report my final answer to 3 significant digits. All right, try both. Which example is the best representation of Charles' law? If the Kelvin temperature of a quantity of gas is doubled and the pressure is held constant, by what factor is the volume changed? So again, we have a factors question here. So if the Kelvin temperature is changed, and we're doubling it. So pick a number, any number. It could be 1, it could be 5, it could be 17, whatever number you choose for T1. I'm going to go with 50 just because. Double it to get T2. So I'm going to have 100 Kelvin. Our numbers can be totally different and we're going to see the same thing. By what factor is the volume changed? So we're looking for what multiplier did we use to get from V1 to V2? That's what our question is actually asking. So I'm just going to use 1 as my V1 here. And we'll plug into V1 over T1 equals V2 over T2. All right, so 1 liter over 50 Kelvin is equal to V2 over 100 Kelvin. To solve this, I have 1 times 100 divided by 50. V2 is 2 liters. So what did we do to our value to go from 1 liter to 2 liter? What did we multiply by? We multiplied by 2. So by what factor is the volume changed? The volume is increased by a factor of 2. If we saw that this decreased, maybe it went from 1 to a half, we had to divide by 2. So it's still changed by a factor of 2. It just would have been decreased by a factor of 2 if we were dividing. Because we had to multiply, that's why it increased. So this seems like a pretty good, reasonable interpretation of Charles' law. The volume will increase proportionally with the change in temperature. So because temperature was doubled, volume is doubled. So this looks pretty good. If the Celsius temperature of a quantity of gas is tripled and the pressure is held constant, by what factor is the volume changed? So we're looking at another factors question here. So T1, T2. We just have to choose degrees Celsius. So I'm going to go with 100 and 200. Again, it doesn't matter what values you change, so long as, oh, sorry, it shouldn't be 200, it should be 300. We are tripling this time. So long as you are abiding by that factor. So we were supposed to be multiplying by 3. Okay. V1 to V2 is what we're going to look at. So I'm going to use 1 liter because 1 is a really nice number to see what's happened. Now, we need to convert these to Kelvin. So 100 plus 273.15 is 373.15 Kelvin. And 300 plus 273.15 is 573.15 Kelvin. Putting these into my formula, I'm going to have 1 liter over 373.15 is equal to, V2 over 573.15 Kelvin. So we're going to multiply 1 by 573.15 and we're going to divide by 373.15. And I get that V2 is equal to 1.535977 liters. Now, with Charles' law, we expected the volume to undergo the same change. That's what we were hoping for. But 1 to 1.535977 liters is not the same. Therefore, this is not a great representation of Charles' law because the fact that the temperature is tripled didn't actually result in a tripling of the volume. It's because we started with the Celsius temperature being tripled instead of the Kelvin temperature. So this is not as great a representation. I would say that our best representation of Charles' law would be our first one because the Kelvin temperature is being doubled, not our Celsius temperature. So let's take a look at a little experiment that can show Charles' law. Pressure is not being changed in this case. There is no vacuum or anything. So pressure is constant in this experiment. And we haven't added gas to our experiment at any point either. We haven't blown up the balloon partway through with our mouth adding gas molecules. So we start with a little bit of water in our flask. We need water. And then we've put a balloon on it. The Erlenmeyer flask is then heated, and we see that the balloon expands. After it's heated, we're going to do the opposite. We're going to cool it in so much ice. So we lay the whole thing in the ice. And what we can see is that the balloon actually gets sucked into the flask. Okay. So the volume of air is changing throughout this experiment, as is the temperature. That's why I know it's Charles' law. So what's happening? So initially, the internal and external pressure of the gas is the same. So the collisions on the inside and the outside of the balloon are equal. So if this was our experiment, the collisions inside and outside are equal. So we're going to have the same number of collisions inside and outside. Let's say this was on our balloon. It shouldn't be on the flask because the flask technically can't expand, but I didn't have enough room. So pressures are equal. As we increase the temperature, the molecules begin to move faster. And so what we're going to see is a increase, let's say we have 4 collisions still on the outside, the external pressure or atmospheric has not changed. The number of collisions inside our flask/balloon have increased. So the pressure inside the balloon, technically not our flask, is greater than the pressure outside, so of the air. Because the pressures are different, this is why our balloon will expand to work on equalizing those pressures. So once those pressures are equal, because our balloon has expanded and allowed more room, the number of collisions will start to decrease. So we have, I think we had 4 collisions on the outside. We're now going to have 4 collisions on the inside. So as that volume continues to increase, the number of collisions between molecules in the balloon decrease, and the internal pressure begins to decrease. Again, comes back down to about 4. The balloon increases in volume until internal pressure, the pressure in the balloon, is equal to the pressure of the air outside again. So volumes stop changing when pressures become equal again. We increase the volume to make more room, slowing down the number of collisions, and so therefore the pressure had decreased in the balloon. So initially the pressure was low in the balloon. We heated it up and we increased the pressure as we heat. The pressure decreased back to the same amount as the balloon expands. So although pressure changed through our experiment, our initial condition and our final condition had the exact same pressures. We need to describe all of this process. Some practice here in your paid Nelson textbook to get used to the idea of Charles' law.